Good morning, good afternoon, good evening. It's been a while. It's been a few minutes. I hate that expression. It's been a couple weeks since my last video. Did a Happy New Year video with the math trick for same tens digits, ones digits add up to 10, one of my personal favorites. You can go back and check that out if you like. And I'm going to do something a little bit different today. I don't think I'm going to look at a specific math trick. Instead, it's MATHCOUNTS season. Some of you may know that already. And my day job is teaching middle school math. And so my students right now, who are particularly gung-ho about mathematics, are working on MATHCOUNTS stuff. So I thought I would pull up some problems. You can see I have in front of me this year's Practice Competition 3. So you can sign up on the Art of Problem Solving website. I'll drop a link in the comments, in the, whatever it's called, the description. So you can check that out there. You can sign up this year and you can take these various MATHCOUNTS practice competitions. So I'm going to look at a couple of the target round questions. The target round questions are calculator allowed, though not required. And I'm going to see how much we can do without a calculator. Not because you need to. Once you need a calculator, use the calculator. But this is a timed test. You only have so much time. And so if we can answer these questions quickly without the use of a calculator, that's even better than if we can do it with the use of a calculator. So I've got Practice Competition 3 in front of me. I've got these target round questions. And I thought a good one to start with would be something like number 3. So the target round questions, I've already said, you get to use a calculator if you want, but also they come in pairs where you have 6 minutes for each pair of questions. So this would be target round question number 3, which would come on the second set of questions. 3 and 4 would come together. Oh wait, but that's not the one I want to look at. I actually want to look at target round number 2. So let's do target round number 2. This would come in the first section. What is the absolute difference between the sum of the first 10 positive multiples of 5 and the sum of the first 10 positive even integers? So, there are a few ways we could approach this. We could actually just compute the sums, right? So the first 10 multiples of 5, that would be 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. Which would not be the hardest sum in the world to compute. I can tell you that it's going to be 275, but maybe something we'd like to avoid if possible. And definitely I could just start typing this into the calculator, right? 5 plus 10 plus 15 plus 20 plus 25 plus 30 plus 35 plus 40 plus 45 plus 50. And whoops, I accidentally mistyped something. There we go, 275, like I said a second ago. We could do it this way. There's no problem with that, right? And then the next step would be, okay, so let's also go ahead and write down the sum of the first 10 positive even integers. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And again, not a super difficult question here. This one ends up being 110. And again, we could come over to the calculator and see that 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 18 plus 20, 110, very good. And of course, if they want the positive difference, then we simply subtract big minus little, and we get 165. But is there another way to approach this? And perhaps you're wondering, how on earth did I know that quickly? There was no magical editing involved. In fact, I'm trying to cut down a little bit on the editing lately just because it takes forever to do. How on earth did I know that that first sum was 275 and then this next sum was 110? So first of all, again, you could totally just pull up the calculator, add these up, and subtract. You have roughly 3 minutes on average for any one of these target round questions, and that's more than enough time to type this in. But what if this came up on the countdown round? So again, for those of you who don't know what MATHCOUNTS is, the countdown round is kind of an exhibition where students go head to head, and they can jot things down on paper if need be, but they're trying to answer as quickly as possible because you're trying to beat the other person to a buzzer and to say the correct answer. So you don't get to use a calculator on the countdown round. Even if you did, I would certainly be able to beat someone who is trying to type this into their calculator. So I think it's worth showing what is it that I'm doing here to get this answer so quickly. And there are two parts to it. Now, part number one is our old friend, the distributive property. Distributive property comes up everywhere, right? Part number two has to do with finding the sum of consecutive integers. So let's actually start there. Let's say I wanted to add 1 plus 2 plus 3 on to some number. In this case, I'll stop at 10 for a reason that you'll see in a second. If I want to find the sum of these consecutive integers, there's this kind of like mathematical legend that goes around. I don't know if it's true or not. It's too good to check. Where Gauss is a school kid, Carl Gauss, a famous mathematician. And his teacher's just trying to get kids off his back. I can identify with that. And so he says to the kids when, of course, they're just working on blackboards, this was a long time ago, hey, add the first 100 integers together, 1 plus 2 plus 3 plus 4, etc., all the way to 100. And of course, most people, they're going to start stacking stuff up and adding. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. But you can imagine if I'm doing this for the first 100 integers, it's going to get a lot more involved than that, right? It's going to take me quite a long time to do it. Gauss, being the mathematical genius he was, even at that tender age, says, oh, the answer's 5,050. And teacher's like, what? How did you get 5,050? So what Gauss says to himself is, all right, so I can write the numbers this way, 1 all the way to 10, all the way to 100, whatever the end number happens to be. But then, of course, I can also write them backwards, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And something interesting happens when we do this, because you might notice, if we think of this in terms of stacking, I get a bunch of the same sum. All of these numbers, now that I've written the list backwards and forwards, have the same sum of 11. And so from there, all I have to do is 2 operations to figure out what the overall sum actually is. I need to count how many 11s are there here. And of course, in this particular case, since we were adding the digits 1 through 10, there were 10 of them. So I've got 10 11s, that's 11 times 10 is 110. And then I just need to remember, well, wait, I got this sum of 110 by writing my list 2 different times. So in fact, I now need to take 110 and divide by 2, and that's where we get 55. Right? So the sum of the first 10 consecutive integers is 55. In general, you can say that the sum of the first n consecutive integers is going to be whatever that number is at the end, because that's how many sums we would come up with if we stacked the list forward and backwards like I did a moment ago, times something 1 bigger than n, presuming we start at 1, because again, that's what's going on with the 11 here, right? We started at 1, we went all the way to 10. When we wrote the list backwards and forwards, it's going to be 1 plus 10 that gives us this number at the bottom that we're going to use over and over again. And then finally, of course, like before, since we are doubling the list to get this product, we have to divide it by 2. So in general, starting from 1, if you want to find the sum of a bunch of consecutive integers, you simply take the last integer, add 1 to it, and multiply those 2 numbers, and then divide by 2. Okay, but what does this have to do with our problem here? Because these are not consecutive integers, right? They're consecutive multiples of 5 and 2. Well, I said we would also use the distributive property. Think about this list up here. This actually is a bunch of consecutive integers just multiplied by 5. If I take 5 out from 5, it leaves 1. 5 out from 10 leaves 2. 5 out from 15 leaves 3. And you can imagine this just continues all the way until we get to the end of the list. And because they said the first 10 consecutive multiples of 5, of course that's going to be 5 times the sum 1 through 10. And then we can do the same thing with our even multiples, right? 2 times 1, 2 times 2, 2 times 3 to get the 6. On and on, all the way down the list until we get to the last number, which must have been 2 times 10. So there are 2 things that you can think of doing here. The first thing I did is I just computed the sum 1 to 10 in my head. It's 55. That's what we see over here, right? We got 55. I multiplied it by 5. 5 times 55. I used a different trick to quickly come up with 275. I multiplied it by 2. For the even integers, that's where I got the 110. And then, of course, they wanted the difference, and so we would subtract. But actually, there's one more thing we can do here. If we know that all of these numbers, 1 through 10, add up to a 55, and we also know that we're just going to subtract at the end, you can actually think of this as multiplying 5 times 55 minus 2 times 55, which itself is another distribution, right? This is the same thing as 5 minus 2 times 55. And so in that sense, the very fastest way to do this is recognize if I'm looking at the first 10 multiples of 5 and the first 10 even integers, and then I'm subtracting, that in fact what I'm doing is finding 3 times the sum of the first 10 consecutive integers. Again, in this case, that's 55, and 3 times 55 is 165. So no matter what way we do it, we're going to get 165. Now again, 3 minutes, we can just type this into the calculator, that's fine. But the principles behind this question and ways to find this answer more quickly or without using a calculator, or even as I did with mental math, can hopefully help us answer more complicated questions that might otherwise take too much time. I hope that's been helpful to you. We'll be doing a few of these in the coming weeks as I continue to coach my own students at MathCounts, so hopefully you enjoyed that. If there is a question that you've had from a recent MathCounts test and you want to send it along to me and see, maybe what's a faster way to approach it or a mental math way to approach it, please feel free to do that in the comments below. Otherwise, I will see y'all next time.